Hey everybody, it's Mr. Peacock here with a video that is just straight fire. That's right, it is off the chain. We're going to be talking about circles. Woo! Okay, was that exciting enough? My producer says it's very exciting and I'm hip and I understand all the cool words that you teens use. So today we're talking about circles. Now, you may recall that a circle is a set of all points in a plane that are equidistant from a given point, called the center of the circle. A circle with a center C is called circle C or circle C. Now, the interior of the circle is all of the points inside the circle. The exterior of a circle is all the points outside of the circle. This seems very easy and obvious, but apparently we have to explain this to you. So, interior, inside, exterior, literally anywhere else. So now that we've gotten through what circles are, so glad, we're going to start learning some actual new terms. The first one we're going to learn is called chord. Now, whenever you hear the word chord, you might be thinking of a G chord or something like that. But in this case, what we mean by the word chord is a segment whose endpoints lie on a circle. Now, there is a very famous chord that is a specific one, much like we would say a square is a more, I guess maybe not famous, but I would say a square is like a more specific version of a rectangle. There's a much more specific type of chord that we know of called the diameter. That's the one that goes through the center. But we're talking about chords in general, and a chord is literally any segment whose endpoints lie on a circle. Please notice it is a segment. Now let's talk about our next word, which is secant. Now a secant is a line that intersects a circle at 2 points. So you might be like, Mr. Peacock, isn't that basically just a chord that keeps going? And the answer is yes. It is a chord that keeps going. It's a line that contains the line segment that would be a chord. Next we have what we call a tangent line. Now you might know the word tangent from when we talked about trig. This is actually the form where that word came from. Tangent. And a tangent is a line in the same plane as a circle that intersects it at exactly and only at 1 point. So a tangent is a line that intersects a circle at exactly 1 point. So it's like if I was to say go off on a tangent by having the smallest thing that I could technically say was related to it. The point where the tangent and a circle intersect is called the point of tangency. That's the point that is, well, right here. That's our point of tangency. All right, so now we're going to talk about congruent circles. This one I think will seem very obvious to most of you, but this is just taken directly from your book. If two circles are congruent circles if and only if, that's biconditional, if and only if they have congruent radii. In other words, if the radius is the same, the circles are congruent because they'll be the same size. And spoiler alert, all circles are the same shape because they're circles. Now let's talk about concentric circles. Now, if you hear the word concentric circles, basically you have enough of them and you have the logo for Target. But concentric circles are coplanar circles with the same center. So notice in this case they are not the same size, but they seem to be both centered at the same spot, meaning the radius of the smaller circle is a part of a radius to the larger circle. And the radius to the larger circle would therefore contain the radius to the smaller circle. Yay! Basics of math. All right, now we're going to talk about what it means if two circles are tangent. So you might remember a tangent line was a line that only touched at one spot. Well, if we have two circles that are coplanar, meaning on the same exact plane, that intersect at exactly one point, so once again touch at only one point, they are called tangent circles. Notice they can be internally tangent. That's where they touch and one of them is inside the other. And externally tangent, that is where they touch and they are outside of each other. If you were to draw a straight line through a radius that would touch the other circle at the point of tangency and continue it going, it would go through the externally tangent circle, and the radius itself would go through the center of the internally tangent circle. Now let's talk about what a common tangent is. You might be able to guess this from the term common tangent. It is a common tangent is a line that is tangent to two circles. In other words, it's a line that it's a tangent line that is tangent that shares that in common between two circles. It's one that is for more than one circle. So in this case, L and M would both be common external tangents to A and B. Now, those are external tangents. You might be wondering, what is an internal tangent? Because a tangent can't go through the circle, but they can cross each other like an X. So if it's on one side of one circle and the other side of the other, so like the top of A and the bottom of B, then that would be what we would call internal tangents for A and B. So they form an X instead of kind of eventually meeting further out. Now, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So what that basically means is if we have a tangent line and then we draw a radius, the radius and the tangent line are perpendicular. The converse of that, which is our second theorem, is if a line is in fact perpendicular then to the radius and the circle at a point on the circle, then it is in fact also a tangent line to the circle. So in other words, if we have two lines, if we have a radius and a line that meets on the circle and that line is perpendicular with the radius, it is tangent. So if we have a tangent line and a radius that meet, then the lines are perpendicular. If we have a line and a radius that meet on the circle at a perpendicular angle, then they are tangent. They're converses of each other. Theorem time. So if we have two tangent lines from the same circle that meet, so, for instance, if we're making those internally tangent lines that are common between two circles, the part that touches from the circle to the point where the two lines meet is going to end up being the same for both tangent lines. So BA would be the same as CA. Now let's talk about arcs. Now an arc is basically a part of a circumference. So here's our circle. The central angle, let's start with that, is an angle whose vertex is, well, the center of the circle of all things. The central angle goes from the center. Now, an arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points of the circle in between them. Basically, an arc is an unbroken part of the circle that goes from one spot to another. So it's not the whole circle, it's basically a part of the circumference. Now, there are a few different types of minor arcs. We're going to first talk about arcs. One of them is a minor arc. Knocking this one out of the park. A minor arc is an arc whose points are on or in the interior of a central angle. The measure of the minor arc is equal to the measure of the central angle. So in this case, the measure of arc AC would be the same as the measure of angle ABC. So a central angle is the same as its inscribed arc. We would name any minor arc by 2 points, being specifically the endpoints. Please notice also the way that we mark an arc is we list it like this. So it's kind of like a line segment, but it's curved. So now let's talk about major arcs. So the minor arc was the part between A and C. A major arc is an arc whose points are on or in the exterior of a central angle. So in this case, from A to C the other way. The measure of this arc is 360 minus the measure of the central angle. So for instance, if this was 30 degrees, this arc would be 330 degrees. Major arcs and semicircles must be named by 3 points. So if we have a minor arc, the one that is less than 180 degrees, that is going to be 2 points, so AC. The way that we can tell that it is a major arc or a semicircle, which we'll talk about next, is there will be a third point, the point that is in between, ADC. What that's telling me is I'm starting at A, I'm going in the direction of D, and then stopping at C. That's what ADC means. Now we're going to talk about semicircles. If the endpoints on an arc lie on a diameter, the arc is a semicircle. The measure of a semicircle is equal to 180. A semicircle is half a circle. So we, in this case, notice once again, we need all 3 points to name the semicircle, EFG. Now let's do this. This is a data application. So the circle graph shows the types of music sold during 1 week at a music store. We're going to find the measure of arc BC. So what we notice here is arc BC is going to be 13%. Now, a lot of you might want to go, oh, that's 13 degrees. But is that correct? No, because if I added up all of these, I'm going to guess, because I'll be honest, I haven't tried it. It's going to add up to be, anyone? Sorry, I'm waiting like it's Dora the Explorer. That's right, I hope. 100 degrees. So in this case, so 13% is just meaning 13% of the circle. So what we would do is we would say 13% or 0.13 times how many degrees are there total? 360 degrees. So we put that in the calculator. 0.13 times 360, and we get 46.8 degrees. Ooh, it's time for a postulate. Exciting. This is called the arc addition postulate. The sum of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. So this is like the angle addition postulate or the segment addition postulate. If we know 2 of the arcs, we can combine them to make our third. Ooh, more theorems. Exciting. So in a circle or congruent circles, congruent central angles have congruent chords. So in other words, these 2 central angles, if they are congruent, the distance from, the distance from D to E is going to be the same as C to B, which makes sense because these lengths are the same and this angle is the same, meaning this has to be congruent to CB. That is angle side. That is side angle side. Exciting. Now here's our next one. Congruent chords happen to have congruent arcs. So if I gave you the ED and CB or BC are going to end up being the same distance, then that means that the arc that created those chords, that is engulfed by those chords, would also need to be the same distance. So congruent chords. Now here's the crazy part. Since we know that congruent central angles have congruent chords, and congruent chords have congruent arcs, then by the transitive property, Congruent arcs have congruent central angles. Yay! So exciting. Sorry, I'm waiting. I'm assuming so much cheering is going on in the class right now. Okay, thank you. It's great. No, seriously, please. Thank you. All right, here's some more theorems. In a circle, if a radius is perpendicular to a chord, then it bisects the chord and its arc. So, in other words, if I draw a radius like this one and it is perpendicular to EF, then I know that this distance is the same as this one and that this arc is the same as this one. In a circle, the perpendicular bisector of a chord is a radius or diameter. That's just the converse of this. These are basically saying the same thing but in opposite directions. And that's it. So thank you all for watching. Please make sure that you do any work that I've assigned if you're in my class. And also, of course, since I am putting this on YouTube, smash that like and subscribe button. Pew, pew, pew. Thank you.